Section 16.5, Curl and Divergence. If f equals pi plus qj plus rk is a vector field on R3, and the partial derivatives of p, q, and r all exist, then the curl of f is the vector field in R3, defined by the partial of r with respect to y minus q with respect to z. For the ith component, partial of p with respect to z minus partial r with respect to x for j, and partial q with respect to x minus p with respect to y for k. The equation for curl can be rewritten using operator notation by introducing the vector differential operator del. If we say that del is the partial with respect to x, partial with respect to y, and partial with respect to z for I, j, and k. So notice that this del operator only has meaning when it is operating on a scalar function to produce the gradient. So we can't really say much about the partials if we're not saying what we're taking the partials of. So if we take del and we apply it to f, then we get the partial of f with respect to x, f with respect to y, and f with respect to z. So what we could do is think of del as a vector with components of partials of x, y, and z, and then consider the cross product of it with the vector field f, in which case we get del cross f. We get the determinant of this 3 by 3. We throw in pqr for f, and what we end up with is exactly what we wanted for curl. So it's basically a short way of remembering it when we say del cross f. So as an example, how about we just find the curl of this vector field? So we'll say that curl of f is equal to del cross f. So that'll be equal to the determinant of, we'll put I, j, and k, and we'll put each of the partials for del. So partial with respect to x, partial with respect to y, and partial with respect to z. And then for f, we have xz for I, xyz for j, and minus y squared for k. So we take the determinant, so for I, that's determinant of this. So we will take the partial with respect to y applied to minus y squared. So that's this guy. And then we'll subtract the partial with respect to z of this guy. So minus the partial with respect to z of xyz. So that'll be our ith component of the curl. And then we will subtract off the partial with respect to x of minus y squared minus the partial with respect to z of xz for our jth component. Remember, j always gets a minus, so we subtract off the determinant of this for j, plus the partial with respect to x of xyz minus the partial with respect to y of xz for our k component. So then, simplifying, we get minus 2y minus xy. When we take our partials for I, minus 0 minus xj plus yz minus 0k, which works out to minus y times 2 plus x for I, plus xj plus yzk. So that's our curl vector. If f is a function of 3 variables that has continuous second-order partial derivatives, then the curl of the gradient of f is equal to the 0 vector. And proving this is not too hard, we just take the curl of the gradient, so that will be the del crossed with the gradient for our vector big F. So what we get is the del in the second row as before, but we get the gradient, which has f's in each of the partials for our third row. So that means that when we take the partial for I, that means that, well, for I, we're taking actually the determinant over here. So that means we take the partial of the partial. So we're taking the second partial of f. So we do that with respect to z and then y. And then we take the partial of f with respect to y and then apply z to it. So that'll be our second term for I. So we do that for each of the components. We do it for I, j, and k. And notice we have equality of mixed partials because we have continuous second order partial derivatives. So this becomes 0, this cancel, these cancel, these cancel, everything cancels, and we just get the 0 vector by Clairaut's theorem. So how about we do an example and show that the vector field xzi plus xyzj minus y squared k is not conservative. So we just found the curl in example 1. I think we said that the curl of f in this case is equal to minus y times 2 plus x I plus xj plus yzk. And notice it's not equal to the 0 vector. So perfect. If it was conservative, then it would be del f for some potential function f, in which case if we took the curl of it, we would have to get the 0 vector, which we didn't. We got this whole mess. So that means that f is not conservative. So we have a pretty quick way of checking if vector field is conservative or not. If f is a vector field defined in all of R3 whose component functions have continuous partial derivatives and the curl of f is equal to 0, then f is a conservative vector field. So notice this is our converse, except that as we've seen before, we don't usually get a perfect converse. We have to make an additional assumption. In this case, we need our vector field to be defined in all of R3 if we want to be able to go backwards and say that the curl of f equals 0 tells us it's conservative. Notice all we proved was that if the vector field is conservative, then the curl has to be 0, but we didn't show that if the curl is 0, then the vector field has to be conservative. We didn't show the other way. So in order to do that, you need this extra assumption, and the proof is not so easy, so we're just going to take it for granted. Let's use it to show that this vector field is conservative in our next example. So let's write out the curl. So we can see that the curl of f is equal to del cross f. So that's equal to ijk. And actually, maybe I'm going to want to spread these out a little bit. So I'm probably going to want more space because look how big each of my components are. So I'm going to write those first. So I've got y squared z cubed 2x y z cubed and 3x y squared z squared. And I want each of these partials. And that's for del, and I need ij and k. So that I end up with vectors when I do my cross product. Okay, good. So now we take our cross product, take our partial derivatives, and we end up with 6xyz squared minus 6x yc squared. Perfect. So that's one down. We end up with 3y squared z squared minus 3y squared c squared. So that's another cancellation. And then 2yc cubed minus 2yc cubed for k. So that's the 0 vector because every single one of those components cancels. And we need one more thing. We need to just make sure that it's defined in all of R3, which notice it is. These are all polynomials for our components. So we could say that our domain is all of R3. And therefore, by our previous theorem, f is conservative, because we had the zero curl and we had a domain defined everywhere. Well, because it's conservative, that means that it came from the gradient of some function. So how about we try to find that potential function? We do it the exact same way as we did before. We just look at each of the partial derivatives. So we'll look at the partial with respect to x, which is y squared z cubed, if this thing is equal to a gradient, which we just showed that it is. And our partial with respect to y would have to be 2x y z cubed, and the partial with respect to z would have to be 3xy squared z squared. So then we'll anti-differentiate with respect to x, and we get xy squared z cubed plus some function of y and z. And we differentiate with respect to y, so that we get 2x yz cubed plus the partial derivative of g of yz with respect to y. So comparing that with our partial with respect to y, we see that this extra function over here must be 0. So we have the partial with respect to y of yz equal to 0. So that means that if we anti-differentiate with respect to y, we get that g of yz must be equal to just some function of z. So that means that we could fill in a little bit more for our potential function now. We know that it's equal to xy squared z cubed, but instead of this function of y and z, now we know that it's just a function of z. There can't be any y's in it. So we'll take the partial with respect to z now, and we get 3xy squared z squared plus h prime of z. So we'll compare that with what we have for the partial with respect to z. We notice h prime of z has to be 0 then. So that means that h of z must be a constant when we anti-differentiate. So we could say that f of x, y, z, our potential function, must be equal to xy squared z cubed plus some constant k. And you could try taking the gradient, and you'll see that it actually is equal to our vector field. Next up, if f equals pi plus qj plus rk is a vector field in R3, and the partial of p with respect to x, q with respect to y, and r with respect to z exist, then the divergence of f is the function of the variables defined by adding all of those guys up. So it's kind of like you take the gradient, and instead of writing the gradient as each of its separate components, you just add up all the components of the gradient when you apply it to the function. So basically what we're doing is we're saying that it's del dot f instead of del cross f. So notice the cross product always gives you a vector in the end, whereas the dot product always gives you a scalar. So the curl is a vector, but the divergence is a scalar. It's something you get by adding up a bunch of things. So divergence is actually pretty easy to calculate. Let's do a quick example. In this case, we want the divergence of f, so that'll just be del dotted with f, where del is all our partial derivatives. So that's the partial with respect to x of the first thing, xc, first component, and we'll add that to the partial of the next component with respect to y. So that's x, y, z. And we'll add that to the partial of the last component. So really, you're just taking each of the partials and just adding them together. And you end up with z plus xz. Because you get z for this guy, xz for this guy, and notice this is just going to be 0 with respect to z. So our next theorem is if we have a vector field in R3 and P, Q, and R have continuous second-order partial derivatives, then the divergence of the curl has to be 0. So to prove this, we look at del dotted with del cross f because that's what we said the curl was. So that means that we are taking the partial with respect to x of the first component of curl, partial with respect to y of the second, and partial with respect to z of the third, and then we add them all together. So we distribute this partial, and this one, and the last one, and we end up with the second partial of r mixed x and y, second partial of q mixed x and z, p, y and z, etc. Notice that these guys are equal by Clairaut's theorem because we have continuous second order partial derivatives, so they cancel. So we cancel these guys, we cancel the q guys, those guys are also equal, just change the order of the partials, and we cancel the p's. So everything cancels and we get 0, exactly as we want. So how about we show that the vector field xz plus xyz minus y squared can't be written as the curl of another vector field. That is, f cannot be equal to the curl of g for some vector field g. So I think we calculated the divergence in the previous example. We saw that that was equal to z plus xz. Notice that's not equal to 0. So how about we suppose that we could in fact write f equals curl g for some vector field g. So we're supposing that it can be written that way. We'll just show this is impossible. Well, this is immediately apparent why it's impossible, because then we would have to have the divergence of f equal to the divergence of the curl of g. But we said divergence of f is not 0. So divergence of the curl of g should be equal to 0 if f is equal to the curl of g. So this is an immediate contradiction. We just proved divergence of the curl of a vector field has to be 0. So the divergence of the curl of g must be 0. But we just said divergence of f is not 0, so there's no way that f could be the curl, because if we take the divergence of both, they should match up. So this is a contradiction. So that means that f cannot be written as the curl of g. Next, suppose a plane region D, its boundary curve C, and the functions p and q satisfy the hypothesis of Green's theorem. Then we have a vector form of Green's theorem. F dot dr, when we take the line integral in the positive orientation, is equal to the double integral of the curl of f dotted with k. So cool. So we have another way of writing Green's theorem. We can do this by regarding f as a vector field in R3 with the third component 0. So we're taking f and we're kind of extending it a little bit. We're giving it r components, but we're setting that r component to equal to 0. So then we have the line integral of f dot dr equal to the line integral of p dx plus q dy. We have the curl we can calculate pretty quickly. We take all the partials, put them in the second row, and we take p, q, and 0 and put it in the third row. So computing the curl gives us the partial q respect to x minus p respect to y. So that means that the curl of f dotted with k is qx minus py for the k component, because that was what we got for curl, dotted with k. So that's great. That means we just have partial q respect to x minus partial p respect to y. So that's exactly what we're throwing in over here, which is exactly what Green's theorem says. Next, we have another way of writing Green's theorem using divergence instead of curl. Suppose a plane region D, its boundary curve C, and the functions p and q satisfy the hypothesis of Green's theorem. Well, then it turns out that f dot n ds, so we have a slightly different form, because over here we had just the f dot dr line integral, so we have to modify it slightly with respect to arc length. So we have f dot n ds equal to the double integral of the divergence. So let's prove this real quick. If c is given by the vector equation xi plus yj for r, then the unit tangent is x prime over the length of r prime plus y prime over the length of r prime for j. Remember, that's just r prime over the length of r prime. We just split it into the components. So that means the outward unit normal vector to c is given by y prime over the length minus x prime over the length of r prime. You could verify that yourself by taking the derivative of the unit tangent and dividing by the length, or you could convince yourself by taking the dot product of these two guys and seeing that they're zero. So if we had some curve c, then some tangent vector, and then some outward normal, they're going to be perpendicular, but however you do it, just understand this is the unit normal vector. So that means that if we're taking the line integral of f dot n ds, we parameterize with respect to t. So ds becomes the length of r prime of t dt, and then f dot n is just p dotted with y prime, because that's what we said n was, and q dotted with x prime for the jth component, and we divide by r prime, the length of r prime, and we still have r prime t dt. So notice that the length of r prime will cancel over here, so we'll just have the numerators, but that's the same thing as saying p dy, because y prime t dt is dy, minus q dx, because that's x prime t dt is dx, which is the double integral of the partial of p with respect to x plus the partial of q with respect to y. So you have to be kind of careful here. Remember, we had, by Green's theorem, p dx plus q dy. So when we take Green's theorem, we would get the double integral over d of partial of q with respect to x minus the partial of p with respect to y. So we have to be a little bit careful over here, because in this case it's dy. Our x becomes a y, and our y becomes an x, because q dx became q dy. So this should be an x. So we have p over x now, we have q over y now, and notice we have a minus here, but we have a plus over here, so that changes this sign, so this sign becomes a plus. So it's not, in the end, exactly what you would expect to have matching Green's theorem, but Green's theorem is used to prove it with just a quick substitution for y and x. This is exactly what we wanted, though, because notice that this is literally just the divergence, which is exactly what we wanted to prove.